Hi guys, I hope you're doing fine as always. Today's lecture is going to be very interesting because we'll be revisiting many things that we have done in the past and we have done in our school days and we have done in the exercises that we have solved in our college academic curriculum, right? Uh, Yes, so this chapter, I'm trying to begin a new chapter today with this lecture. So this chapter, it's more like a warm-up exercise, right? So that you can develop better understanding of the system, the kind of system that we are dealing with, and it would open your gates of imagination, right? So that you're able to visualize uh, the dynamics of the system or how the stars behave in the systems, the how the particles behave in these systems that we are dealing with, right? Because it's very important to develop this way of visualizing things so that the theory, the idea, the concept, it sticks to your mind, right? Moreover, again, we will start with from the very basic understanding and from the very basic problems, right? Because once you fully understand the basic stuff, then you can develop onto more complex problems, right? And then you can try and solve them and see what result you get. For a given problem, we'll try to attack that problem with different approaches, right? So that because it's important to be creative, right? And tackle the same problem from different angles so that you develop a better understanding. And that's how you develop interest and be more creative in physics, right? Also, again, the most important things, we'll solve numericals and problems, and I hope you guys do, right? So let's start. Yes. So what are we aiming to study at? So we will try and solve. We'll try and solve for different orbits of individual stars in a given potential, right? So we will see how orbits look like or how orbits behave, what are their properties and the parameters that are conserved or the parameters that in fact we can talk about for a given potential system, that how stars move around in that system, right? Also, we would try and look for possibility of different orbits in spherically symmetric systems and axis symmetric systems and bar-like mass distribution, for example. So, for example, let's take example of our Milky Way. So this thing right here. So this galaxy that I'm showing, it's Milky Way. The first image on the top, it's the edge-on view, and this image over here, it's a view, side angle view for the Milky Way galaxy, right? So this right here, you're viewing galaxy as on the disk, as if you're in the plane of the disk, right? So this center bright sphere that you see, it's called the bulge. So basically this point over here at the center is where it's claimed that the black hole sits for the Milky Way, the Sagittarius star black hole, right? And all this brightness comes from the weird motion of so many stars that are, have this weird, rigorous motion around this black hole, and they're just moving, and it's the complex motion, the complex trajectories that they have, right? Then this over here is the disk. Our sun, our solar system sits about 8 kiloparsecs away from the center of the Milky Way. So somewhere over here, probably, right? The brown stuff that you see, it's the interstellar gas medium. So our Milky Way, like any other galaxies, has stars, has dark matter, right? So dark matter, so this, for example, if this is the Milky Way, so the dark matter, it sits in the halo. So so this is the bulge, this is the disk. Or apart from the bar that we have in the disk also has spiral arms. So though being axially symmetric, our disk, it also has spiral arms, right? So this makes our life more complex but interesting. And this halo basically means the dark matter halo or the stellar halo that is surrounding the visible galaxy, right? But apart from the dark matter halo, the stars, we also have the gas in the medium. But in study right now, we are not dealing with gas. We are just talking about the stars, really, right? So the idea of undertaking such studies is that, or any studies, that you predict a model to match with your observations, right? So, for example, you're far off in a galaxy and you observe this galaxy and you observe the stars, the velocity of these stars and the motion of these stars, and you see the how the orbits look like, etc., etc. And after you have all the models, for example, you have spherically symmetric model of the system, you have axis symmetric model of the system, right? When you have the velocity and you have the orbits and you have the energies of all the stars, for example, the probability distribution function of all the stars, for example, let's not get into details, you try to match those observations with the models in hand that you have, right? And then the best model that you know of would, then you would claim that your model matches the, for example, the type of galaxy that you're dealing with. And then you say, okay, then it's a, this observation corresponds to a spherical galaxy, for example, or an axis symmetric galaxy, right? So that's why but to match this model, it's important to know these models beforehand, right? So you should know how to deal with these models, or what are all the parameters in the model that exist, right? The assumption that we are making here again is that galaxy is smooth. So though this brightness can be broken down into individual stars, right? All this brightness comes from the stars, basically, apart from the gas, right? But since there are so many stars in the galaxy, it's really moving as a bulk. We consider galaxy smooth, so that our derivatives that we take with respect to velocity or with respect to position, for example, are valid everywhere, right? So we are not dealing with any irregularities or clumps, though we know that there are subhalos in the galaxy, right? So apart from this clumpiness in the bulge and in the disk and the spiral arms, for example, there are irregularities, right? Even in the space that is surrounding this galaxy, the dark matter halo, as we say it, even the dark matter halo, it's clumpy because it's believed that there are subhalos, tiny spheres of dark matter halo that are just, swimming around in this pool of dark matter, right? But that's not a concern right now. We're just going to develop our basic understanding from the very basic potential and mass distribution. So let's consider our first potential example, which is static spherical potential, right? This is the most easiest potential that you can imagine of. So and since it's spherical potential, so we'll be restricting ourselves to spherical coordinates, because in the spherical coordinates, our mathematical equations would become most simple and most easy to visualize and to solve, right? Suppose this is your frame of reference and your star sits at r radius distance away, right? So this r vector over here, it's for the coordinate of the star, right? And since it's a spherically symmetric potential, the potential depends only on r, the radius away from the center, right? Your center is over here. So even the force per unit mass here would also depend on r and not on any other coordinate, right? We know from our basic classes that equation of motion for such a system that depends only on r is given by d square r over dt square equals f r e r cap, right? So this e r cap over here is the unit vector in the direction of radius, right? So that's one. Now let's try and see that how the total time derivative of r cross dr by dt behaves, right? So this r cross is the position vector, and this dr by dt, it's basically the velocity vector in the radial direction, right? So we are trying to calculate r cross v, and you probably might have gotten the hint that r cross v, it's basically angular momentum, right? So let's see how this behave. We are just revisiting this problem. I think we already know that what's the fate of this term would be. So now I'm just applying the chain rule. So ddt, in the first term here, the ddt acts on r, and in the second term, the ddt would act on this, keeping the r cross same, right? So we get this. Now the first term, of course, this term is 0 because the cross product of any vector onto itself is 0, right? So a cross a is 0 here, dr by dt cross dr by dt is 0, plus r cross d square r by dt square, right? But from equation 1, we know that d square r by dt square equals force per unit mass time, force per unit mass, right? So we just substitute that with the er cap that comes in the equation. Now er cap and r vector are pointing in the same direction basically, right? So again, so r and fr, this product, it's non-zero, but since there's a cross product involved and it's of the same vector, this term becomes 0. This means that d dt of this term is 0, which basically means r cross dr dt, it's constant, and as we call it, it's angular momentum. So the conservation of angular momentum basically tells us that, of course, the modulus of this term r cross dr by dt is constant, but also since it's a vector, it must always lie in the same direction. The direction of the vector should not change. This means that the orbit of the star lies in a plane, right? Because r, it's in this direction, and dr by dt, the orbit, the star, it's moving like this. This means the velocity vector, it's in this direction. And r cross v, if you do the right hand thumb rule, would give you L, right? And the L, it's conserved. So the magnitude of L is constant, but also the direction of L remains constant, which means that the orbit lies in a plane in a spherical potential, right? Now we can do this with the Lagrangian approach. So as said, that we would try to tackle the same problem in different ways, just to be a little more creative and be a little flexible with the problem, because we are not really trying to derive anything, we are not really trying to reach somewhere, we are just trying to explore the problem in hand, right? So let's try this Lagrangian approach now. So we know that the Lagrangian in a coordinate system is given by the canonical kinetic energy minus the canonical potential energy. So by canonical, basically I mean that how the potential energy or the kinetic energy is defined in that coordinate. So in spherical coordinates, the kinetic energy is this term over here in the bracket. So so r dot is basically the radial velocity, and this term over here, r square psi dot sine square theta, it's basically the azimuthal velocity plus the r square theta dot square, where r square theta dot square is the polar velocity, right? So I've written the coordinate transformation from Cartesian coordinates to spherical coordinates here. I'm sorry. So this psi, it's azimuthal angle, and it corresponds to phi over here. So this is basically, so this psi, it's basically psi and psi here. And again, I'm so sorry for my stupidness. So this is psi again. So psi is the azimuthal angle that goes from 0 to 2 pi. Please do not confuse this with the potential phi, right? Though we usually write potential as phi, capital phi actually, and then the azimuthal angle again as phi. But right now I'm just taking it to be psi. This is a mistake. So the psi, it's the azimuthal angle that goes from 0 to 2 pi, and theta, it's the polar angle that goes from 0 to pi, right? Now we know the Euler-Lagrangian equation of motion, which is the total time derivative of partial derivative of Lagrangian with respect to canonical velocity q dot minus the partial derivative of Lagrangian with respect to the canonical coordinate, right? So I over here corresponds to the particular coordinate that we are dealing with. So for example, in Cartesian coordinate, this I goes from 1 to 3, meaning x, y, and z, right? So let's try and solve for Euler-Lagrangian equation of motion in for r coordinate, right? Yes, so this equation over here becomes d dt of del L over del r dot minus del L over del r, right? And I would really appreciate you guys if you try and solve this yourself and see where you reach, and maybe if it takes you to pause the video and then you match it with the final solution over here, though it's just a 2 to 3 step solution, but still, I mean, that's how you would really build up your confidence of solving problems, right? By doing it yourself. So just whenever you think that you can try and solve something, and you can try and give it a go, just pause the video and try and do it by yourself. So this equation over here, so del L over del R dot, where L is given by this is the partial derivative, so we just get R dot in the first term, minus the partial derivative of Lagrangian with respect to R, and we end up obtaining the terms in this curly bracket, and this is equal to 0 again by the Euler-Lagrangian equation of motion. Now this term over here, it's dr dot by dt, which is basically the acceleration, which is similar to what we had in our last slide over here. So this term d square r dt square corresponds to the dr dot by dt that we have, right? So it's the double time derivative of r, or the single time derivative of r. So it's tackling the same problem with a different approach really. Minus the term over here, and then I take the del phi by del r term on the right hand side, and we know that that force per unit mass, it's basically minus derivative of phi, right? So I can equate this term over here to force per unit mass, and again, since phi depends, the potential depends only on r, so will the force. Now let's try and solve this Lagrangian equation for psi, the azimuthal angle. And when you will do that, you would end up with this equation over here, right? So again, which basically means that r square psi dot sine square theta, it's constant, right? Now let's restrict ourselves in the plane theta equals pi by 2, right? So theta equals pi by 2, which means that we are in xy plane, right? And see what this equation becomes. So if we are in theta equal to pi by 2 plane, which means theta, it's constant, right? Which means time derivative of theta would vanish. So this equation over here becomes this equation 1 right over here, and equation 2, it's over here. And then again, the angular momentum, we relate this r square psi dot with the angular momentum L, right? So equation 1 and equation 2. Please pause the video and try and solve it yourself if you must. It's a straightforward calculation though, right? So the angular momentum that we get, it's the r square psi dot. Now let's see what happens to the energy. So let's try and analyze these equations that we had further. This is the approach that is taken in many topics, or in many different topics that when we deal with, mostly in classical mechanics, for example. So always we can write up to our convenience. We can write this, for example, here we can write this total time derivative in a different form. So for example, here d dt, I can write it as d d psi of d psi by dt, right? So a very informal way of putting it is that the d psi gets cancelled, and then you recover d dt, right? But this is just really another way of writing d dt. And psi here in general could be any other coordinate that your actual function might depend on. But right now, since I know what I have in mind, so I'm just writing d dt as d psi over d psi by dt, right? And I know now this d dt was the operator, and now this d d psi becomes the operator that would act on your function, which would sit here, right? And the d psi by dt just basically comes on the left hand side, and this d psi by dt, it doesn't act on anything, the d d psi does, right? But I know that the d psi by dt, which is psi dot, equals L by r square, right? So I just substitute that thing over here, and now the equation 1 that I had over here can be solved using the same approach, right? You can pause the video and again try solving it. It's a pretty straightforward calculation. In the middle, you would want to convert, make the substitution of r equals 1 by u, right? So wherever you have r, you substitute as 1 by u, which means that dr by d psi becomes minus 1 by u squared du by d psi. So this substitution of in an equation of motion, substituting r as 1 by u, it's very famous. If you remember from your elementary classes or from your college lectures, that this substitution was used while studying Kepler orbits, for example. And this, in fact, this substitution, it's used almost everywhere when it comes to solving spherical potentials. For example, it is used in general theory of relativity while you're solving for Schwarzschild black holes, for example, or any other thing. So this is a very, very famous substitution that we are making, right? So once you use this d dt as L over r square d d psi in the equation 1, and you substitute r for 1 over u, and your dr by d psi derivatives change, right? And then you, since L is constant, L comes out of all the derivatives. You end up with an equation that looks like 3. So force that depended on r now depends on 1 by u, right? Now this equation, we will later we will solve a problem using this equation. It's a very important equation, right? So this equation, instead of being in r, it's in u, and instead of being with respect to time, the derivatives with respect to time, it has derivative with respect to psi, the azimuthal angle, right? Now this equation in many cases can be analytically solved, and in many cases, depending on the function of potential or force per unit mass, right? If the potential, it's simple, sometimes it's analytically solvable, this equation, and you get an absolute analytical solution for r. And sometimes it's not solvable and you have to numerically integrate it and see the orbit evolve, right? But one thing that we can predict is that for bound solutions, r and u would oscillate, right? If the solutions are bound, the r and u would oscillate. And for the unbound solutions, that means the solutions that go out of bound, for example, if r tends to infinity, the u would tend to 0, right? So these are the kind of tests that you can do when you know the potential, right? But what we are aiming at right now is to see what happens to the energy, right? So let's multiply this equation 3 by du by d psi and integrate over d psi. So you can note down this equation and try and do this integration yourself. So I'm multiplying by du by d psi in this entire equation, here, here, and here, and then integrating over d psi, right? So again, so this is what the equation would end up looking. So in a very informal way, again, what you basically do is that you cancel this d psi over here, and etc., right? In the first term, you try and rewrite this term over here as half of d psi of du by d psi whole square, right? So if you would open this up, if d psi acts on this, you would get 2 du by d psi times d square u by d psi square, right? So if you would just open up this derivative over here, if d psi acts on this, times 1 by 2, you should end up obtaining this term over here, right? So I'm just rewriting it so that I can get, so basically I'm trying to write it in a way so that my d psi gets cancelled, and I just get the d of some term, so that the integral of d some term, it's basically the term itself, right? So for example, if you have an integral of d of sine theta, for example, so this integral of d sine theta would basically be sine theta, right? So that's exactly what I'm trying to do here. And this over here, the d psi gets cancelled, an informal way of putting it, and then you end up with u du. Now this integral, it's doable. And over here again, minus of integral of f of 1 by u square du, and we know that L is constant, so this integral again depends only on u, so it's doable. Now when the d psi gets cancelled in the first term, you end up with d of some term, and the term, it's written just like that because the integral cancels with the total derivative, right? So you end up with half du by d psi whole square plus u square by 2 comes from here, minus 1 by L square goes out of the integral, L is constant, integral of f as a function of u by u square du plus the constant of integration. So all the constant of integrations that come by solving these integrals are stored in C dash. Now making the substitution of u equals 1 by r, right? You can do that substitution here again, and eventually when you do that substitution in force and in u square and du, everything gets replaced by r using the substitution u equals 1 by r, right? And you end up with plus 1 by L square integral of fr dr, right? So this plus comes because u equals 1 by r, so du becomes minus 1 by r square dr, right? Plus the constant of integration. Now we know since fr, right? So since I don't think I've written it here. Yes. So from previous slide, and we already know that fr is minus del phi by del r, right? So this means that phi, it's minus integral of fr dr, right? So that's exactly what I've done here. The fr dr is the minus of phi r over L square plus the c. Now the c dash becomes c because the integral, this integral would give another constant of integration, right? And we have this term over here on the left hand side, right? So we can rewrite this equation as du by d psi square plus u square plus 2 phi by L square, everything gets multiplied by 2, equals c, this term over here, and that I write as 2e by L square, and I call E as the energy, right? So again, if energy is less than 0, that means you have bounded orbits, right? The orbits that don't just fly off, or the trajectories that just don't go like parabolas or hyperbolas, for instance. And if E happens to be greater than 0, then you have unbounded trajectories, right? So 2e over L square equals 2 phi over L square plus u square plus du by d psi square. So it's basically calling that energy equals the potential plus the kinetic energy, right? Though that there is the derivative with respect to psi, it's not with respect to t, but it looks like that this term over here has to be kinetic energy, right? Because we know that the energy, the total energy of the system, it's the kinetic energy plus the potential energy, and the potential energy is stored in this term. This means this term is the kinetic energy of the system. Now also we could have done this the easier way, since we already know the Lagrangian, the energy or the Hamiltonian, it's basically kinetic energy plus potential energy, right? We know that, but we just wanted to take a much more longer way so that we can explore more things on that path. So also, since Hamiltonian, it's time independent, right? The Hamiltonian or the energy depends only on x, the position and the velocity. This means energy is conserved. So the angular momentum is conserved and the total energy is also conserved, right? And it's given by kinetic energy plus potential energy. Yes, so don't look. So now let's try and solve this problem, that find the potential corresponding to the trajectory given by r equals a exponential of b psi, where b is a constant, a is a constant, psi is the azimuthal angle, and r is the position, right? So try and solve it by yourself. Don't look at the solution that's here. Just hide it or pause the video and try and doing it yourself. The hint is that you could use this equation 3. In fact, you just substitute what's given in the question in this equation, and you would end up obtaining the potential, right? So just pause the video and try this question yourself. The hint is over here. Okay, I hope you've paused the video and tried doing it. So the solution, it's given right over here. You take the derivative of this term over here with respect to psi and multiply it by 1 by r square, so that you end up with an equation that looks like equation 3. And on the right hand side it becomes this, right? The b comes downstairs and you multiply by r square. Now you take the d over d psi derivative of this term again and you multiply it by L square over r square this time. And on the right hand side you take the d over d psi derivative of this term, right, and you multiply it with the L square over R square, right? And you know from your equation 3 that this term equals force per unit mass, which is R, right? Now E, B, psi is written as it is, and you try and combine the other thing, which is L square B square over R to the power 4, right? Times A, B psi, and from the equation you know that A, E, B psi is basically equals R, so R and R to the power 4, it gets cancelled, right? And you end up with L square B square over R cube, which is force. Again, you know from the equation 3 that you had previously, and you know that force equals minus d phi by dr. So which means that this term over here equals minus d phi by dr. Now you just need to integrate it to obtain phi r as L square B square over 2R square plus C, where C is the constant of integration, right? Yeah, one thing I'm not sure. I think I solved it incorrectly. I think because you will have to recheck. I think I've made a blunder here, because when you take the d, so when you have this equation and when you take the d psi, when you take the L square R square times the d psi of this equation, right? Yeah, so that I mean you would have to take the derivative on the r square as well, right? I'm not sure if I've taken the derivative of r square also, so you'll have to check that. Yes, I don't think I have. So maybe this would end up completely in a different way, so you'll have to solve. This time you'll really have to solve it, because I'm not sure about this one. I think I'll try and rectify this error in my next lecture. Okay. I hope you understood the problem. So basically the problem was that you were given a trajectory and you were trying to solve for the corresponding potential, and it becomes really easy if you plug in this equation in equation 3, right? Now the typical orbits and spherical potentials are in the form of rosette. So they are not exactly circular, they are not exactly elliptical. It really depends on the initial condition. But one thing that we can say that in general they are rosette, that looks like of this form, but they are planar, they remain in the same plane. But then the trajectory may in general look something like this. Now let's do one of the application for spherical potential, which is Kepler potential, the very famous, where force goes as minus gm over r square. The equation 3 in that case for Kepler becomes this equation over here, right? D square u over d psi square plus u equals gm over L square, where m it's the total mass of the system that we are dealing with. And our star, whose orbit we are trying to calculate, it's a test mass, so we don't really care about it. And m, it's the total mass of the system in which we are trying to calculate the orbit of the star, right? Now gm over L square, since L is a constant, m is a constant, and g, it's the gravitational constant, so the right hand, it's a constant. So it's basically the double derivative equation that it's analytically solvable, and we know that the solution looks something like this. So it's something that we know that d square u of d psi square plus u equals, so this is a harmonic motion equation, if you remember, right? So that's a very famous equation that we deal almost all the time in physics. And as an exercise, I leave to solve this equation, and you would end up with an equation that looks something like this, right? Where C, it's the constant times the cos psi minus psi naught, where psi naught gives the phase of the motion, plus gm over L square, right? Now one of the parameters that we define for orbits is the eccentricity. E, where eccentricity it's given by the epicenter distance, which is the farthest distance that is possible in an orbit, minus the pericenter distance, which is the most closest distance possible in an orbit, over the epicenter distance plus the pericenter distance, right? So this is something, eccentricity is something that we are familiar with. It tells us about the orbital property, that what kind of orbit it is. For example, for a circle, there is no concept of farthest point or the most closest point, right? Because all the points on a circle are equally distant from the center. That's how we define the circle, right? That's the basic definition of circle. For ellipse, though, the eccentricity may vary between 0 and 1, right? So what I mean is that your trajectory may look like this. And for example, if this is so basic sun earth system, right? So this, we know that sun sits here in one of the foci of the ellipse, and earth goes around on an elliptical orbit, right? So the epicenter, it's the most farthest distance from the sun, and the pericenter is the most closest distance from the sun, right? So my diagram sucks a little bit over here, and it might look that this is the pericenter, but yeah, I mean, so the basic idea is that the pericenter is the most closest distance, and the epicenter is the most farthest distance from the center, from where we are measuring the distance, basically, right? Now the epicenter is basically where the maxima of the r sits, or the distance sits, right? And we know that the maximum of r corresponds to the minima of u, because r equals 1 over u. So where r is maximum, u in the denominator has to be minimum. And looking at equation A, it can easily be evaluated that the u is minimum for cos psi minus psi naught becoming minus 1. That means psi minus psi naught has to be pi, right? And you can, so when substituting cos psi minus psi naught as minus 1, you would get u as minus c plus gm over L square. And that would give you, the inversion of u would give you r as 1 over gm L square minus c. Similarly, for pericenter, the minima of r corresponds to the maxima of u, right? And the maxima of u occurs when cos of psi minus psi naught, it's 1, which means psi minus psi naught is 0. And you get the pericenter distance as 1 over gm over L square plus c, right? Now, when you try for eccentricity, when you substitute this epicenter, pericenter in this eccentricity equation, you end up with eccentricity as c L square over gm, where c is this constant that was appearing in the equation, right? Now, you can also solve for the semi-major axis, which is basically the r epo plus r peri over 2. So the semi-major axis, it's basically the half of the most, basically the most longest, the longest diameter that exists in the orbits corresponds to the major axis, and the semi means that that major axis, the longest diameter that exists in the orbit, has to be divided by 2. And when you substitute for the same, you would end up with L square over gm times 1 minus e square, right? Now what we see that from our previous study is that energy and angular momentum are called integrals of motion, or the constants of motion, right? Because L is constant, it's conserved. E, energy, it's constant and is conserved. In many cases, there would be that only energy gets conserved and angular momentum, it's not conserved, right? For example, in axisymmetric potential, only the z component of L, the angular momentum, is conserved, and the other two are not conserved generally. And in the generally, but if you're on the plane, for example, of the axisymmetric potential, for example, in the case of Milky Way, if you're on the disk, then most certainly all the three, the total angular momentum is conserved. Otherwise, it's only the z component that is conserved. But for spherical system, all the components of angular momentum are conserved and the total energy is conserved as well, right? So it becomes really simple to solve for such orbits in which you have more integrals of motion, right? Okay, so let's try and solve for another problem. So show that for Kepler orbits, that sine of psi minus psi naught equals LR dot E over GM. So I would really like you guys to stop to pause here and try and solve for this self. It's pretty easy. the hint is you just have to take the time derivative of a, really, because if you take the time derivative, the cos of psi minus psi naught would basically becomes sine of psi minus psi naught, and then you can solve for sine minus psi naught. And otherwise I have solved it for you anyways, and it's a pretty straightforward numerical, right? Okay, that was all for today. So it was just a little warm-up exercise, really, just so that you get a little flexible with things and see how it's done. In the next lecture, I would try and make more graphs, and so that you can actually see the things happening, right? Well, thank you so much.